This video covers the section 8.2 least squares regression in OpenIntro statistics. The main purpose of this section is to take what would be more of a subjective way to fit lines to data. So if we look at a scatter plot of data, so if we look at this example for instance in figure 8.11, if we look at this cloud of points, we might think, well, there's a lot of different lines we could fit to that data. And here in this example plot, we have actually a couple examples of how we might fit lines. There's a variety of other ones. Maybe those two lines to your particular view are not quite optimal. Maybe you tweak them a little bit. But we want to have some kind of objective way to fit these lines. Some way that we can at least agree on as reasonable and as a repeatable process. And that's what we're really trying to do with section 8.2, which is least squares regression. This is a particular method for fitting lines to data. And so the context for this section is to look at gift aid for freshmen at Elmhurst College. So gift aid is basically financial aid for college students going to Elmhurst College. So this is a pretty interesting data set where the college actually released the information about family income and gift aid that the university gave to the student for a particular family. And, this was anonymized. You're not going to know who is who. So if we look at the data here, things make sense. So higher family income tends to correspond with less gift aid. And this is pretty typical for universities. If a family has a lot of income, it tends to be that a student will receive basically a smaller amount of aid from the university. And that said, there's a lot of variability in this data. So if we look, for example, at this point, which is at about a little bit over $200,000 for the family income, and it's about $10,000 in gift aid, it's quite different than if we look at another point here, which is at maybe about $220,000 for family income and about $24,000 for gift aid for that particular student. So even if we compare two students, we do see some variability that is not necessarily perfectly consistent with that more family income corresponds to more gift aid. It's a little bit more volatile of a process. And you think this makes sense as well because we have different factors that come in for gift aid. So for instance, the scholastic achievement of the student, how what are their SAT scores if that's relevant for this particular university, and what is their GPA from high school, and what other accomplishments do they have? And so these all are factors that are going into this gift aid calculation, or at least probably are going into this gift aid calculation from the university. But we are just focused on this single predictor of family income. So we're not going to capture the perfect process for this gift aid estimate from the university, but we're still going to do some prediction here. So that's kind of the context for this initial section 8.2.1. And in section 8.2.2, we start talking about, how do we actually get to that objective measure of how do we best fit that straight line to the data? And there's a couple examples here that are discussed. The first one is, well, if we look at the residuals from one of these lines, we could think, well, we want to minimize, the distance between our line and the actual observations. When we're fitting a line, we're kind of intuitively trying to think like, how do we get this line so that it is close to the actual points in the data set? How do we get the line to fit the points in this scatter plot here? And if we just think, well, we want to maybe minimize the total sum of distances from the line to the points, that's one way to create optimization or a way to design what is the best fitting line. And another way is to, instead of just looking at the distance between the lines, is to look at the square of the distances between the lines. So in that context here, if we're looking at a point that is maybe about $4,000 from the line in the vertical space, then that would be a quarter as bad as a point that is maybe 8,000 from the line fit. So basically, if you go out twice as far from the line, that's 4 times as bad. If you go out 3 times further from the line, that's 9 times as bad. So we're basically trying to get points close to the line, but also really try to keep from having any particular individual points super far from the line, because there's a very large, you might think of it as a penalty associated with that kind of outcome. So the line can get pulled a little bit more aggressively if there's a point that is further from the line that we're fitting. And so that process of using that squared distance and trying to minimize the sum of the squared distances of the points from the line, that is the vertical distance, that is actually the criteria that we use for fitting least squares regression lines. And this is one of the most common criteria for fitting regression lines. There are other contexts, and this first one that I mentioned, just using the absolute distance and trying to minimize that absolute distance, that's also used in statistics, but it's not quite as common. So noting here on page 318, some of the benefits of this particular least squares criteria is that it's the most common method used. Also, computing the least squares line is widely supported in statistical software, so there's no special program you need to write to use this particular criteria for fitting your data. Also, in many applications, a residual twice as large as another residual is more than twice as bad. So in this example here, we have like maybe being off by 4 is more than twice as bad as being off by 2. And so if we square the residuals to account for that kind of intuitive penalty for having our point far from the line, that's a good way to kind of account for that aspect. When we are fitting least squares regression lines, there are some conditions that need to be met, and there is some flexibility on some of these in some cases, but some of them are much more rigid than others. So the 4 criteria are linearity, so that the data needs to show a linear trend if we're going to fit a straight line to it. We also have this criteria, nearly normal residuals. That said, there are plenty of cases where this isn't quite as important. I'll talk about that more in a little bit. But if we have a relatively small data set, then it is particularly more important. There's also constant variability. So what constant variability here means is that if we look at maybe the left part of the data, here I'm going to scroll up to the plot. If we look maybe over on the left region, if we look at how variable they are around the line, it's not that different than if we looked at another part of the plot. Like if we looked over on the right side, the data are relatively the same kind of variability from the line. And in this graph, we see that roughly speaking, the data are roughly the same variability around the line as we go across from left to right. So that's what it means for constant variability. We'll see some examples later on one example later on of what would be a case of breaking that condition. The 4th criteria is independent observations, and this one, like many other methods in the book, is really important. If the individual observations in the dataset are not independent, the methods that we're using here are, I would say, tricky at best. So one particular caution is that if you have time series data, if you're looking at maybe a sequence of events that take place, one kind of very canonical example would be like we have data measured each year, and maybe the data for 1 year tends to be closer to the data for the next year. So the observation in maybe year 2018 is relatively close to the observation from 2019, and this tends to be true if we look at any pair of adjacent years. So in that case, our observations wouldn't be independent. They would have some correlation that is in the sequential nature of the data, and that would be very problematic. That's probably the most common case that you'll see for where independence is not valid is in time series data like that. So here we actually get to look at some cases where these criteria are being broken. So in this first plot on the left for figure 8.12, we're looking at basically a data set where it's very clearly not a straight line trend. So we see a lot of curvature in the overall trend of the data. And we have kind of this shading to help it be especially clear that there is this curvature going on. And if we fit a straight line to that data, well, it fits fine in some areas, but if we look in other areas, it fits pretty badly. And this makes a lot of sense. You can't fit a straight line to super curved data and expect it to be a great representation of that data. So that is a case where that first condition had failed, that linearity condition had failed. And in the second example, we have, again, thinking about the nearly normal residuals. Here we have a lot of data that is relatively clustered around the line. It looks like pretty good consistent variability. And then we have this outlier point. And that's typically the kind of thing that we're going to see for, or one of the common cases that we'll see for deviations from normality. And as I had mentioned earlier, the strictness of that criteria, I would say, is less important than the strictness for the other criteria. The other three criteria, I would say, are more important than this normality. Although, again, with the caveat that if you have smaller data, then that normality aspect becomes more important again. In the third plot, we're looking at an example of where constant variance for the data is breaking. So looking at over on the left part of the plot, the data is relatively tight around the line. If we look further right on the plot, we're seeing basically the data starting to fan out. It's a lot more variable on the right side of the data of the plot than it is on the left side of the plot. And so this is a case where we don't have constant variability for all the different values of x. We're seeing that the data tends to be more variable for some x around the model fit than other values of x. And here in the fourth plot, we have what looks like more time series data. So this is kind of where we see an additional trend in the data, especially. So here we have something where it's maybe we see some type of linear downward trend. But if we look at sequential observations, we see that they tend to be clustered together much more tightly than the overall clustering of points around the line. Going over to section 8.2.4, so finding the least squares line. So we have this line that we're trying to fit to the data using the least squares method. And we need to estimate our parameters, our beta 0 and our beta 1 parameters. So if we would take some of the statistics associated with the data, in our plot, we can actually compute our least squares regression line estimates of beta 1 and also beta 0. So beta 1, our point estimate of that, so B1, is equal to the standard deviation of the y values divided by the standard deviation of the x values times the correlation between the x and the y values. All right, so like I was saying, the estimated value of the beta 1 can be directly computed just by using the standard deviation of y divided by a standard deviation of x and multiplying that by the correlation value r. So that gets us our slope of the least squares regression line. And next, we also need to compute the y-intercept of that line. So that's the beta 0. So if we want to do that, well, another property of the least squares regression line is that there's a particular point of the data that is always on the least squares regression line. And that is the point that is the x value of the mean of the x values of the data and the y value that is the mean of the y values for that data. So basically, if you took the average of the x values and you looked at the average of the y values and you plotted that as a point on your graph, that point is going to definitely be on the least squares regression line. So if you think way back to algebra course where there was the point slope form of a line where if you had the slope of a line and you had a point on the line, then we could use that to write out what the line the formula for that line would be. Yeah, that's what we're talking about here on page 320, is using that point slope form for a line, which hopefully sounds at least a little bit familiar from algebra course. But right, so if we wanted to basically compute the different parameter estimates of our least squares regression line, we can, again, first estimate that slope parameter by using the standard deviation of y divided by standard deviation of x and multiplying that all by the correlation R. Then second point is, well, we know that the average values of the x's and the average values of the y, if we take that point, that's going to be on the least squares regression line. Then we can use the point slope form of the equation and write out the equation of that line. And lastly, to get it into our form that we like to have, where we like to have y on the left side of the equation and y-intercept on the right side plus the slope times the x value, well, we can then just simplify the equation by solving for y here from the point slope. And we basically end up with our parameter estimate of the y-intercept, the b0, as the average value of the y's minus b1, which we've already estimated, times the average of the x values. So that's the actual calculation. And example 8.10, so that walks through an explicit implementation of that method for the Elmhurst data. So follow along there for sure. Make sure that this makes sense to you, that walking through those 3 steps for fitting a line makes sense. And in practice, we don't in practice actually do these calculations by hand. And in practice, we tend to use statistical software to estimate, to just do this all for us. So we feed in the data and we say, hey, basically give us a least squares regression line, and the software gives us out these parameter estimates. But it is important and useful to know kind of these background properties of the least squares regression line, so you get some intuition about what's going on here. All right, so this is an example of some computer software output where if we fed the data in and we said fit a least squares regression line, it would tell us what the y-intercept should be. It would also tell us what the slope should be for the line. All right, it's actually example 8.11 talks a little bit about the different columns of the software output. So let's actually take a moment here and look at this. So if you've gone through the inference sections of the textbook already, then you'll have heard or seen this standard error statistic that is often associated with a point estimate. And so that's what this second column is that we basically get standard errors associated with each of our parameter estimates from the statistical software. And then we also get, if you've gone through the inference for the numerical data chapter, at least the first section of that chapter, you'll have seen that we talk about t-values. And so we basically compute t-values for each of our different parameters, and then we look at the probability of basically the p-value for those particular t-values. And in general, it's very rare that we actually care about the standard error and t-value for the intercept. Our main focus is usually just on the estimate, standard error, t-value, and p-value for the slope. We care about the actual value of the intercept because we might want to write down the equation, but we tend not to care as much about the statistical significance of the intercept. The intercept is, we tend to think of that as just how much should we move the line up or down? Whereas oftentimes when we're thinking about the slope is reflecting what is the relationship, or how strong is that relationship between the outcome that we're predicting and the predictor that we're using to predict that outcome. So basically in this case, we're looking at, is the p-value is telling us the strength of evidence that there is a relationship here between these two particular variables is there a linear relationship in particular between these two variables? Hopefully the scrolling isn't bothering anybody too much. Right, so example 8.12 is talking about a particular case now. So let me just read it out. So suppose a high school senior is considering Elmhurst College. Can she simply use the linear equation that we have estimated to calculate her financial aid from the university? She may use it as an estimate. So the answer is yes, she may use it as an estimate, though some qualifiers of this approach are important. So first, the data all come from one freshman class. And that basically, what the university does for how they compute financial aid from one year to the next may change. So that line is, our estimate for that particular year. But here we're thinking about a student for a future year. So it's important to think about, this is the context of the data. So for statistics, we're often thinking about not just, fitting a line and getting a prediction, but we also need to think about the context of the data and how appropriate that model is for using for a context. So in this case, we have data that is fit for 1 year, which maybe that's a reasonable, at least ballpark estimate for a future year, but we need to keep in mind that the university may change what they're doing. And so there is this caveat that we need to consider. And second, which is also particularly important, is that the equation will provide an imperfect estimate. The equation is focused on looking at the trend in the data, not at predicting the precise value of individual students' aid. So we talked about a little bit earlier that there's probably a lot of factors that are going into how the university is calculating aid. And those additional factors are not being incorporated into this simple model, this simple linear model of just one predictor value. So we talked as well about how one student to another student might have similar family incomes, but they might get different values of aid. And so that's just an important consideration here, which is typically true for a lot of linear models and a lot of models in general, is that the predictions for a particular observation may be imperfect, even if we have a good sense of overall what is happening with the data. All right, so interpretation. So section 8.2.5, interpreting regression model parameter estimates. All right, so we have these two model parameters. B0 is 24,319. B1 is negative 0.0431. So what do these numbers really mean? The practical interpretation of these numbers is to, I guess the one that we often focus on the most is the slope. Well, we will also talk about the intercept, so that's why we've put it in this order here. We're going to talk about the slope a little bit first in this example, example 8.13, and then we talk about the intercept, and that's just kind of an order of priority of what's usually most important. But so thinking about the slope, so the slope is telling us that if a person has $1,000 more family income, we can think about what is the actual estimated change in the aid we would expect for that student on average. So very roughly, kind of what kind of change in aid would we expect? So if we take $1,000 and we multiply it by our slope, so we're kind of taking an x value and we're shifting it over by $1,000. So we're basically multiplying it by that slope. We're going to say that the predicted y value is going to be about $43.10 less. So that's basically saying that we expect that for each additional $1,000 of family income, we would expect a student to receive about $43.10 less in aid on average. And that on average, consideration is important. It may not be perfectly true for any particular student. Again, we don't have privy to the way that Elmhurst College was doing the exact calculations. We're just doing a model here that tries to get some sense of what the relationship is here. So, right, that interpretation of that slope parameter is often really emphasizing thinking about, okay, if we change the x value by some amount, how does the y value change? That's how we tend to interpret the slope parameter. Then we have the other term, the intercept. So this is basically describing the average age if we had an x value of 0. So in this particular context, basically if the family income for a student was $0, so that family had no income, then how much would we predict that student would get in aid from Elmhurst College? And so the intercept is 24,319. So we would be predicting that the average aid for such a student would be about $24,319, plus minus some error for that particular student or uncertainty for that particular student. So this actually makes sense. This intercept is something that is practical and interpretable for this particular example. That said, in some applications, the intercept has no, practical value of interpretation. So if for a particular application, there really are never observations near where the x value is, the x value never gets close to 0 or never can take a value of 0, then it makes much less sense to think too highly or think too much about the meaning of this intercept. So that's 8.2.5. 8.2.6, extrapolation is treacherous. And this is something that, is not just true in statistical modeling. This is true in life in general, right? Like you take some information and you're thinking about how might it apply to some loosely related context. If we think about it in that regard, that's a form of extrapolation from our information. And the further we think out from a related context, the less relevant it's going to be. For the information that we have to, is less relevant to that further unrelated context. So I think this quote is great from Stephen Colbert. So this was back from 2010, talking about how some different news channels were discussing the blizzards on the East Coast in the context of global warming. So the quote is, "When those blizzards hit the East Coast this winter, it proved to my satisfaction that global warming was a fraud. That snow was freezing cold. But in an alarming trend, temperatures this spring have risen. Consider this. On February 6th, it was 10 degrees. Today, it hit almost 80. At this rate, by August, it will be 220 degrees. So clearly, folks, the climate debate rages on." So this is a great example of extrapolation. So Stephen Colbert is taking two data points. February 6th, it was 10 degrees. And when he made this quote on April 6th, it was almost 80 degrees. And he's drawing a straight line between these 2 points. And he's now taking that line and thinking about where that line goes and where is it going to be in August. He's extrapolating out from the region where he has some data and saying, where is that point going to end up? And, he's clearly making a joke here where if we do that extrapolation, oh my gosh, it's going to be 220 degrees. And, the ridicule here is that the way people often think about weather and think about climate change is that these are two very different things. Weather changes day to day. Climate is a long-term trend. And so looking at these individual observations is really not important. We need to look at the overall trend for global warming. So that I think is an excellent quote about taking the big picture rather than just being so myopic about what is happening today. All right, getting into a little bit more here. So I think one fun example of thinking about the Elmhurst data is that we can plug in a family income of anything pretty much. So a family income of $- probably doesn't make a lot of sense, but we can think about a family income of a very large amount. So in example 8.14, we're looking at if we would take our data. So actually, let's go, I'm going to scroll back up here to the plot of data, just so we can talk about that for a moment here first. So if we look at the plot, the actual data is ranging in values from close to 0 all the way up to close to $300,000 for the family income. So our support of our data is about $0 to close to $300,000. And if we think about extrapolation is about taking our line that we fit over data like this and kind of going beyond the bounds. So going further to the right of where we have data and imagining that our model that we fit will continue out just as a straight line as we have for the data over that we have in the particular region. So if we think about taking this line and extrapolating it all the way out to say $1 million for a family that has income of $1 million, this is extrapolation out far beyond where we have data. And this is what we're talking about when we're saying that extrapolation can be treacherous. It can be very risky to take a model fit for a particular set of data and then try to apply it to a context where we don't have much, if any, data. So if we would do that, if we would take that family income of $1 million and we would have put it into our model, we would find that on average, the model predicts that the student will have negative $18,781 in aid. Well, Elmhurst College doesn't offer negative student aid. The model doesn't make sense anymore when we extrapolate out so far. And this is an example where we can see that very clearly, that extrapolation just doesn't make sense. But it's just kind of a general lesson that if we do extrapolate out from the type of information we do have, and we go out very distant from where the information we do have, kind of the things we've learned from our data may not apply in that new context. All right, hopping into section 8.2.7, using R² to describe the strength of a fit. So R² is a statistic. It is computed as literally just the correlation squared. So the correlation is the value given the value R, or at least that's the value that's the symbol we use in our book for the correlation. And so R² is just the correlation value squared. And this particular statistic has an important actual interpretation. So it is representing basically what fraction of variability in the Y values are being explained by the model. So let's see here. How best to make this super clear? So we have this mathematical representation of it, but let's come back to that here in a moment. So if we're looking at our plot here, if we forget about the x values, we just think about how variable is all the data across all the different y values. Don't worry about where they are on the x value for a moment. It's pretty variable. It ranges from about $5,000 in gift aid all the way up to $32,000, $33,000 in gift aid. So we're seeing maybe about maybe most of the data falls within about 10,000 to about 28,000. So maybe about 95% or so of the data is falling within about an $18,000 window. Now let's look at the data and how closely it falls along the model itself. The data tends to be closer to that model, that line that we've fit to the data. And if we look at it, it tends to be, for the most part, within about plus minus maybe $6,000. So in that case, we've taken, if we took a random student originally and we just said, okay, roughly how much do we think this student might be getting? It's probably, in the range of $10,000 to $28,000. So about an $18,000 window. But now if we know how much family income they have, we're able to get a more precise estimate of that student's likely gift aid from the university. So maybe we're going from about an $18,000 window down to about a $12,000 window for our prediction for that student if we knew their family income. And so in this way, we're saying that the model is explaining a portion of that original variability, that $18,000 window variability, down to that $12,000 window variability. That's kind of the intuitive way to think about it. It's kind of a fuzzy math way to think about it, but we'll get into the math here on page 323. So the actual R² is being computed as the variability that is explained by the model itself. So for the calculation, for the simple calculation of R², we just take the correlation, so about negative 0.5, and we just square it, we get 0.25 for R². And that happens to correspond very precisely to, if we looked at the variance of the actual aid values, the actual y values of our data, and we subtract out the amount of variability still left in the data after we fit the model. So this is the variance of the residuals from the model. So we basically are taking the difference of these two things. So, and then we divide it by the original variability of the y values. That corresponds to the r squared value. So again, let's walk through this, because this is an interesting concept, and it's not one that's, I think, easy to grasp. Is that, again, looking at the data, student gift aid is ranging for the most part from about $10,000 to about $28,000. We have a window of about $18,000 of gift aid if we ignore the trend, if we didn't have any idea of what a student's family income would be. But once we know a student's family income, we can predict their gift aid a bit more precisely. We're not going to predict it exactly, but we get a bit more precise of an estimate. We get, maybe about a $12,000 window around the line. So if we knew a student had a family income of, say, $50,000, then, the model says that our estimated gift aid for that student, our average gift aid for such a student would be about $22,000 or so. And the variability around that, maybe plus minus 6,000. So kind of a window of 12,000. So when we're talking about r squared, we're talking about how much, we're basically talking about taking that $18,000 window and shrinking it down to that $12,000 window. We have a more precise estimate. We have a better sense of what that student is likely to get from gift aid. That's the intuitive way to think about what r squared is telling us. And it is quantified using variance, which is a little bit less intuitive of a way to think about it. But that is a kind of standard in statistics where the math works out really nicely. And that's why we often see variance as something that is used oftentimes in calculations, is that the math works out very beautifully. And it also is a very, working with variance is kind of a I would say, more advanced piece for students who are, as they get further into statistics. Like, the importance of variance is something that comes up quite frequently. So, well, we see it here a little bit. We don't go into it a ton in our book, just because it's a little bit beyond an intro statistics topic, but it is an important concept and aspect. So think about the, how much variability of the outcome is being predicted or explained away by the model. That is what r squared is representing. And again, the calculation is just the correlation squared. All right, on to section 8.2.8. So this is a fun instance. So we've talked a lot about, or at least some about, using a numerical value to predict another numerical value. But in some cases, we have non-numerical values where we're trying to predict numerical values. So categorical data, our predictor may be categorical data. And one example here we have, which is for eBay auctions for the video game Mario Kart for the Nintendo Wii. So this is a bit of an older data set, but it's a really, I think, enjoyable data set to look at, where we have a lot of different variability. We have a lot of different variables that might be influencing what an auction might end up at. And one of those variables is whether the game that is being sold in this auction is used or new. And of course, intuitively, this is going to influence what how much somebody is going to spend or bid on the game in these auctions. So in the scatter plot here, we have our predictor is now just this categorical used or new. And then we're looking at what is the total price of the auction. So this is the final auction price plus the shipping price. And as you might think of intuitively, we see that the auctions for new, sealed versions of the game tended to be higher than the final auction value for used copies of the game. So the way we typically do this in practice is basically we code our categorical data to have numerical values. So we basically use, in this case, we're using the value of 1 to represent if the game is new, and 0 for if it's used. So you can think of 1 as being the game is new, 0 as being the game is not new. So when we're doing categorical data, especially if it's just two different levels, we just think of it as 0 and 1. If we have multiple categories, then it's a bit more complex, and that's something that's touched on in the next chapter. But so just focusing on this context of a categorical variable with two outcomes. So if we take our categories and we code them as 0 and 1, now we basically have made this to be a numerical case. We have our predictor being either 0 or 1, and now we can actually think about just fitting the line to this data. And in this case, we fit a line where we fit the final total auction price is, if we do our least squares regression line for this data set, it's about $43 plus about $11 if the game is new. So if the game is used, then we think of the value of cond new, this cond new variable being 0. And so then we do $43 plus $11 times 0, so really just $43. So used price, the average used price is $43 or $42.87. And if we look at the average new price, then we would have $42.87 plus $10.90 times 1. Again, we take the coded, what are called the coded values for the categorical data that we have made as numerical values, and we can plug that into the formula. And these coded values of categories is a way to have our formulas still make sense, because it's weird to put in an actual category into a formula. So if we code our categories as 0 or 1, we basically are able to kind of use our typical framework for least squares regression and regression generally. So that's how we handle categorical predictor variables, is we again are coding those those categories, again focusing on the case where we just have two categories. One of them gets coded as 0, the other one gets coded as 1, and now we use those numerical coded values to fit our line. So I think that is the end of this section. So hopefully this was useful. This is, again, a kind of new format and something that, is kind of an author's commentary on the section and what is important, and kind of walking through the different concepts. If you enjoy this, please, add a comment, give it a thumbs up. That will help us know that this was actually useful. I think a comment in particular would be helpful to let us know this was actually useful. If it wasn't useful, also add a comment. Let us know, what would be more useful. I'm sure I didn't explain everything super clearly, but hopefully it was, useful to kind of hear some additional commentary on a particular section and how these things are relevant and how we think about them as well. So a textbook is written very linearly, and I think this video format of talking about this section gives a little bit more opportunity to break that linear format and have a little bit more of a conversational format. All right, well, with that, take care, and look forward to trying more new things in the future.